Yeah.
Hi everybody. Welcome to November's edition of the Schuler Observatory Public Open Night. So thank you everybody for coming. And those of you watching the recording of the live stream, welcome as well. It's my pleasure this week to introduce my colleague Chris Mendillo, who has freshly returned from New Mexico, where he has recently flown UMass Lowell's balloon observatory.
Right. Right. Thank you.
So take it away, Chris.
All right. Thank you, guys. Thank you. Thanks, Silas. Thanks, everybody, for coming. Hello. Anyone online watching? All right. I see some young astronomers in the crowd. So either of you guys know what this is a picture of? If you can guess it, then you're... Whoa! That's a good guess. It's a good guess. It's not a supernova. It is a picture of a star. There's a star in the center of this picture, where that little picture of the star is. But it's being blocked out, so you can't see the star. So do you have an idea of what these things might be? They're kind of going around in a circle around the star.
Other stars?
There could be other stars. That's a good guess. There could be other stars. There's systems of stars, multiple stars that orbit each other. How about this? What's the closest star to Earth?
Sun.
Yes! That, most college kids don't get that right. What goes around the sun?
Planets.
Okay. Do you know what those are?
Planets.
Those are planets. They're going around another star. That's not our sun. This is a star that has a very unfortunate name, which is HR 8799. And this is a picture taken, a series of pictures taken over 7 years from one of the biggest telescopes on Earth, the Keck Observatory, which is in Hawaii on a mountain called Mauna Kea. And you can see the time running down here. We've been taking these images for 7 years, and you can actually see the planets. There's 4 planets in the system, like Jupiter. They're big, bright, gas giant planets that are orbiting around this star. And in order to see them, you need to block out the light from the star because it's very bright. One of these planets is typically up to 1 billion times dimmer than the star that is in the center of the system. These planets are in a very young system, and they're very warm. So they're emitting a lot of infrared radiation, and that's what lets us see them from the ground. With a big telescope and an infrared camera, you can see that the light that these planets are actually emitting, and they may only be 10,000 times dimmer than the star that they're orbiting. But that's extremely bright as far as exoplanets go. So these are what we call exoplanets. We know about thousands of exoplanets, but only very, very few of them have ever been imaged directly from the ground. We've never done it in space. Maybe we did it in space once with Hubble. There's a disputed planet around the star Betelgeuse that Hubble took a picture of, and it was there, and then it wasn't there. So we're not sure about that. Would be a very different kind of planet than the planet in our solar system. These are planets sort of like Jupiter in our solar system. This is, for scale, 20 astronomical units. So an AU is the distance from the star to the sun to the Earth. So these are orbiting at around 15 to 20 out to 80 or so AU. So they're like the planets in our solar system. So like I said, it's very, very hard to take pictures of these. The big challenge is that the star is so bright and the planets are so dim. This is the Keck Observatory where this was taken. There's 2 8 or 10 meter telescopes there made of these segmented mirrors. This is on top of a mountain, so you get very good, reduced. I'm surprised there are actually clouds in this picture, but I guess it does get cloudy there. You're up above a good deal of the water vapor and everything in the atmosphere, so you get pretty good, what we call seeing. The stars don't twinkle as much as they do on the ground. Okay, so, again, you've seen this already. All right. No one else was at the other one, right? Sorry, same thing. You know all the answers to all my questions. This is, so I said we know about a lot of exoplanets. We've discovered, the first exoplanet we discovered was in 1985. And so this is really new science. We've only known about these planets. We've thought they were there for a long, long time, but we never discovered them until 1985. This is a collection of data. It's a simulation, but it's driven by data of measurements made by the Kepler Observatory, which was a satellite that we flew. I assume some people here know about Kepler. Kepler discovered planets by using what's called the transit method. So this is where it would just stare at one patch of the sky and observe maybe 100,000 stars and wait for a planet in each star, around each star, to go in front of the star and eclipse the star. And then the star would get slightly dimmer. It looks like this. So you can imagine, this kind of looks like Mercury transiting the sun. We don't get to see this, we don't get to see the disk of the star and the disk of the planet going in front of it. We are so far away that all we see is this dot of light in the sky, which is just a star. And if we can just measure how bright it is in time, we'll see the brightness dip slightly and then come back up. And we would know that is from the shape of this, what we call light curve, we could determine things about what was eclipsing the star, and if it's a certain depth, and you can, you know how bright the star is, you can figure out how big the planet is, and the mass of the planet, if it's a planet or a binary star or something like that. But in this sort of measurement, it's typically a planet. Observations like this are very rare, because if you think about the geometry that you would need to get this measurement, you could only do it for stars in systems where the planets orbit perfectly edge on to our line of sight. Okay, if the system were face on like that first image I showed you, the planets would never eclipse the star. So only very, 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 very small number of stars happen to have the right alignment. It's completely random, right? The right alignment where their planets will eclipse the star from our point of view. And still, we've seen thousands. The picture I just showed you is, this movie I just showed you is every orbit found by Kepler, where it shows, each system is, the stars in the center, and it's showing the planets and their relative sizes and temperatures and as they go around. So we've found thousands of these planets. We've found maybe 4,000 or 5,000 planets since 1985, but still it remains elusive to take an actual picture. What we're trying to do is make the first steps towards taking an actual direct image of a planet like Earth that's orbiting another star in our galaxy and be able to learn things about it. To do this, you need to go into space, because a planet like Earth orbiting a star like the sun is 10 billion times dimmer than the star, which is just an incredible difference in brightness. And trying to actually see this next to an extremely bright star is next to impossible, and you need a very, very powerful instrument to do that. The goal would be to take an image like this and do some classic astronomy to it, put a spectrograph on there, and measure the spectrum of the planet. So this is telling you about the atmosphere of that planet. You can see on the vertical axis here is planet-star flux ratio times 10 to the 9. So this is already a billion, one up here is a billion times dimmer, and it goes down to 10 billion times dimmer than the star. And this is what Earth would look like from a distance. And we could see molecules causing these absorption features in its spectrum. And this would be the reflected light from the planet, because Earth is very cold and does not emit a lot of thermal radiation like those hot Jupiter kind of planets do. So we have to use reflected light, and we have to work in the visible, or in the very near infrared. And this is what the goal is for the next 20 years. NASA wants to build in 2040, 2050, a big flagship mission to do this, to take this picture and make this measurement and look and say, oh, this planet has ozone, or this planet has methane, or this planet has carbon monoxide. And maybe they'll find a molecule that could only be produced by life, called those biotracers or biomarkers. And then we would know that there's a planet, that planet has life on it. We don't know what kind of life it is, but we know it would have life. And that may be one of the first ways we are able to tell that there's life on other planets. So I was telling you this is hard to do. The reason it's hard to do is because even if you have a big telescope, there's this nasty fact of life, of wave physics, the fact that light is a wave, and you have a circular telescope that has a hard edge to it. When you try and take a picture of a star, you don't just get an infinitely small point of light, you get this kind of wash of light that goes all the way across your camera. So you have this bright peak in the center, and you see these ripples, and those ripples just go out forever. And it's due to the process of diffraction, which has to do with the wave of light refracting or diffracting off the edge of this pupil, this telescope mirror, and you get this very wavy pattern. So this is a picture of a star and a planet. Does anybody see the planet there? No? It's there. It is. But it's a billion times dimmer than the star. So there's no way the projector, right, could ever display it. This is a really, really short exposure. So this is 0.0001 seconds of an exposure. So if we try to take this picture from our telescope here, we'd have to take a very, very short exposure to not have this star completely swamp the detector and saturate it. So in order to see the planet, we could say, okay, let's turn up the exposure time. So if you want to do that, and you want to see a planet that's a billion times dimmer than this star, you would need to take a 10-second exposure. And if you did that, it would look like this. The star would completely swamp the detector. It would saturate. There's no detector on Earth that has enough dynamic range to take this picture and see the star and then see the planet next to it. Never mind all the problems of trying to see a very dim thing on top of a very bright background. There's just no way you could ever do it. So what you need is a special instrument that's called a coronagraph. And a coronagraph can block the light of the star without blocking the light of the planet. And that's what we've been building here at UMass Lowell. It's what we've been flying on a series of experiments going back to 2005, where we flew it on a sounding rocket mission, and now we're flying it on a high altitude balloon. And the idea there is you would then, that instrument could block out the starlight and dim it, and then you'd be able to see this planet off to the side. So the instrument we built to do this is an observatory called Picture-C. The acronym means something about imaging planets, but picture is, obvious. We're trying to take a picture of other solar systems. This is picture floating at an altitude of 127,000 feet above New Mexico. This was live video from our recent flight, which happened in September 28th of this year. So we were just out in New Mexico launching this. You can see us proudly flying the UMass Lowell flag. And you can see that at 127,000 feet, the sky is black. And we're above 99.9% of the atmosphere. And if you think about that, the fact that it's roughly 40 kilometers. So at 40 kilometers, you're above all the atmosphere, for all intents and purposes. Our atmosphere is only 40 kilometers thick. Our planet is 6-something thousand kilometers in radius, right? So if you take those proportions and imagine what it's like, an apple, right? If the apple were the Earth, the skin of the apple would be our atmosphere. That's how thin and tenuous our atmosphere is. We have this tiny thin blister of air keeping us all alive. And that's what we're dumping everything that we produce into and breathing. So we should remember that even this simple picture from our telescope gives us a lot of perspective on where we are and what we have to do to keep this this little thin atmosphere that we have. This is picture. So it's this big telescope that is in a truss structure that we built here in Lowell. We have this welded at a shop near, we work in Waterrancet Mill, so our lab's in the basement. We have this welded at a shop down the street, painted at a local auto body shop, and then we design all of this stuff in-house and have it built at various machine shops around the state. Our telescope sits in a pointing system that's designed by NASA. It's called WASP, and it can point the telescope at any star in the sky. And the whole thing sits on this big platform called a gondola, and there are cables that run up and they attach to the balloon. And the balloon is way, way, way above us, and the balloon is huge. This whole thing weighs 6,000 pounds. It's enormous. It's extremely heavy. The balloon that lifts it, when it's fully inflated, is over 400 feet across in diameter. So if you imagine like a football stadium or a soccer stadium, the bowl of the stadium, this balloon is big enough to just fit in that bowl. It holds 40 million cubic feet of helium, which takes 2 semi-tractor trailer trucks, tankers of helium to fill up. We flew once in 2019. We had a delay in 2020 because of COVID. We tried to fly in 2021 again, but we had bad weather, and we were there for 6 weeks, and we ran out of time, and we had to go home. We came back in 2022 and got a successful launch. This is it in real life.
Why September?
September is the only time of the year from this site where we can launch because of the wind. So there's just kind of yearly weather patterns that roll through this part of New Mexico. And it has to do with the surface level winds. You have to worry about the wind. All we talk about is wind when we're down there. The wind from the ground all the way up to 100,000 feet. And the hard thing about getting off the ground is the wind from the ground up to 1,000 feet, because the balloon, all the cables and everything is 1,000 feet long. So the wind could be completely dead, stopped still on the ground, but 100 feet up, it could be blowing at 20 miles an hour. And if you put a balloon when it's not partially inflated, it's still 50 feet across, it's this big sail, and the wind would just blow it, and it would be not safe. So they have very strict rules about when we can launch, and September's the only time. So this is the real thing in real life. This is without all of its thermal insulation that we wrap around it to keep it from getting too hot in the sunlight. And these are the people that built it, color-coded by our helmets. So Superior Chakrabarty, Professor Chakrabarty, is the PI of the mission. He's the head honcho of the mission. I'm here, this is Kurani Hirwasam and Glenn Howell. They were both grad students at the time. They both got their PhDs working on this project. Glenn is in London doing a postdoc, and Karavi is here doing a postdoc, and he's still working on the mission. The UMass Knoll, Jason Martell is our mechanical engineer. He and I designed everything you see, and he figured out how to put it all together. Did a ton of mechanical engineering and simulations to figure out if it would work. And this is what we do. So we put this whole thing in a truck and we ship it out to a place called Fort Sumner, New Mexico, where there exists a small barn on the side of an municipal airport that's not used for anything anymore, that NASA currently inhabits. This is the vehicle assembly building down there. It needs a new paint job, obviously. But we go here, and this is where we are, in Fort Sumner, New Mexico. Population has been decreasing, which is good for us, down to 1,031 people. It's a very desolate place. It's just a road. There is only one place to stay, the Super 8 Motel. This is where you live when you're there. It's not the greatest accommodations, but you look like winter every now and then you see a balloon launch across the street. It's a beautiful place in its own way, but there's just not a lot there. All the restaurants close at 3 p.m. There's no real way to eat dinner without being creative and cooking for yourself, but you know, it could be worse. So every day we drive across the street. We see all sorts of incredible creatures everywhere, giant grasshoppers, whatever this thing is. This thing was just sitting on a case when we walked in the lab one day. It's a giant moth. It's like this big. It's the size of a small bird. Lots of strange creatures to contend with when you're down there. Sometimes you drive to work and there's a 200-car man train that just sits in front of you for 10 minutes and you have to wait and you think you're back and forth all day long. It's a strange place to be, and we send our grad students out there for 6 weeks at a time to try and launch one of these balloons, see if things just go down further. I don't know what's on there. You can drive out to the wind farm. This is all there is to do. Look at the propellers going, the windows going. That's the logo. Forget about that. You can drive down to Roswell, New Mexico, and see you can do a lot of research at the UFO and Alien Museum and Research Center. They have a library there. It's a very highly regarded research institute, clearly. The reason we're there is it's really dark and there's nobody there. You can take this picture with your cell phone. This is the picture I took, put my cell phone on the roof of my car and took a picture. And you see something like that, or you see something like this. You see the entire Milky Way, more stars than you could ever count. You might see something like this. Does anybody know what this is? kind of. It is a UFO. We know what it is, so it's not you, but it is a flying object. Our friend who owns Twitter now knows what this is. So this is Starlink, the Starlink communication satellites that provide internet across the world. Happened to launch one of their constellations of 54 satellites the day before we got out there. And we're driving, and we just happened to look up in the sky and see this thing flying over our car, and we pulled off the road and got out and watched it fly over. It was very unsettling to see. We weren't sure what it was at first, but then realized quickly what it was. So after all the waiting, you actually do get to launch one of these things when the wind is just right. You might do this 5 times, so we'll go out and try and launch, and we'll be all ready, and they'll say, sorry, too windy. But every now and then, they don't say that. They actually take the balloon out of the box and start blowing it up. So here's the balloon, here's one of the tanker trucks filling it up, there's another one on the side there. There's this long train of plastic. This whole thing is made out of like Ziploc bag plastic. And it ends here. So this is all balloon on the ground, but it's empty because the helium is gonna expand as it goes up, and it's gonna fill up this volume. So they just fill up this bubble at the top. And then you can see our parachute is here. That's what brings us back down to the earth when they decide the mission's over. They'll push a button and we just drop, we free fall, the parachute opens and we land. There's that big launch vehicle that you saw, kind of for scale, which is huge, is sitting way out on the tarmac here, holding our telescope. And when everything looks good, they'll give the cue. There's a guy named Larry driving this truck.
Okay, give me the balloon.
He says, okay, give me the balloon.
Coming to you then.
The guy says, coming to you, Larry, and they'll pull a cord there and release the balloon. And so this thing goes up, there's this collar around here that'll pop off. You can see that in the next video. Pretty beautiful, you can see this bubble of helium. You hope that nothing goes wrong right now. And then Larry drives the launch vehicle around, like literally looking up, trying to get underneath the balloon so that when he lets the payload go, it doesn't swing and smash into anything. And that has happened. If you Google Australia NASA balloon launch, you'll see a video of it happening. And so they're very, very concerned with us being safe here. So you can see he popped what's called the pin there, and we're free, and we're floating up above the launch facility. You see this big tarp that they lay out, they put that down and then put the balloon on top of it. That thing that just flew by was that collar that keeps the balloon all cinched up. That's me, right there. Our grad students are on those stairs there, and then you can see Fort Sumner, the Pecos River Valley, which is what creates all the green, the runways from the airport, and we drift up, and it takes about 3 hours to get to our final altitude. This telescope has one of these instruments that's called a coronagraph I told you about to block out the star. And so that's our mission. We go up and we take pictures of stars and we try and block them out and see either planets or dust or asteroid belts around those stars. We fly a path like this on the ground. So this is the ground track of our flight. This is the first one that we did, where we flew kind of just over Albuquerque and ended up to the west. In the last flight, we did something very different. This time of year, the wind at high altitudes is just sort of randomly distributed and kind of just blows you around in some random paths. You take these circuitous loops and zigzags around. We were headed straight for White Sands Missile Range, which is where they do a lot of missile testing, and they didn't want us to get too close to that. And there's not really a great place to land after you get over that. So they brought us down here on this nice, soft, grassy field at about 2 o'clock in the morning. So what did we actually accomplish? A lot. I'm not going to go into it in too much detail, but we did demonstrate a couple of things for the first time ever. This is the image of the star. The color scale is weird. It's not black and white, but it's colored. And it is showing you there's a star here in the middle, and we're blocking out a lot of that light. If we didn't have this coronagraph instrument, this whole image would be red. The whole thing would be red. We're blocking out a lot of it to get it down into this dark green, this green color. And then we're doing something even more special with our instrument. We have this little mirror that can change its shape and create a very dark zone called a dark zone on this side of the image. And so we're doing that, you can see how this side is much darker than this side. We're doing that in flight. And that's never been done before from a telescope that wasn't bolted to the surface of the Earth. We're trying to demonstrate this technology to one day fly one of these flagship missions. This is the first demonstration of it ever in flight, and so we're really excited and happy about that. And we're going to keep flying this, and that's the goal. I mean, that's the great thing about this. You saw it comes back down, it lands on the ground, we pick it up, it dust it off, literally vacuum it out, but completely undamaged. And fly it again. We have a grant to continue working on this and upgrading different aspects of it and keep flying it. We're going to fly it 2 more times within the next 5 years and hopefully actually take this picture where this thing will get really dark. We'll take very long exposures. This is only a half a second. We can take that 10-second or 20, a minute-long exposure and see maybe a ring of dust, like an asteroid belt, or maybe even a dot. That's a planet. And that's all I had for you. Thank you. I'll be happy to answer any questions you have. Questions? Anyone? Yeah.
What kind of upgrades are you doing?
So we're putting in new cameras, kind of across the board, much more sensitive cameras. We are adding, I told you in that class about these deformable mirrors. There's these mirrors that can deform their shape. We're adding a second one of those, which will allow us, in that image that we took, I showed you how it's dark on one half of the image. That'll allow us to make the whole thing dark, so that we don't have to worry of, oh, is the planet on this side of the star or on that side of the star. The whole thing will be dark and we'll be able to take the picture like that. We're adding a bunch of new control algorithms that incorporate machine learning, and we're doing a new technique for being able to look for planets around binary stars. So this coronagraph thing can only block the light from one star, and if there happens to be a second star in the system, like an Alpha Centauri, which is like the closest star to Earth and the Sun, and probably has planets, but has a binary companion that's pretty bright, and its light will interfere with our measurements, so we need ways of blocking out 2 stars at one time at the same time. So we're testing a new technique for doing that. Yeah.
How many stars did you observe this time? Or are we expecting any results to come out of it?
Out of this flight, it's unlikely. We had a lot of interesting dynamics during the flight. The whole balloon is hanging on 1,000 feet of cabling. It's swinging underneath, the telescope is swinging underneath the balloon. There's a lot of disturbances that happen, and we're learning more and more about them. And no one's ever done anything close to how precise this is from a balloon. So we're learning a lot. The NASA guys who build the pointing system, we work very closely with them to figure out like how stably they can point the telescope and how we deal with transient little vibrations. So there was a lot of that happening during the flight, so we could not observe for very long. We would get the whole thing aligned and working, and then 30 seconds later it would kind of get hit and everything would get misaligned, and then we'd have to spend another few minutes realigning it, and then that would happen again. So it just kept happening over and over again. We've already got 100 new ideas of how to deal with that in the next flight, but we were limited in what we could do to address it during this flight. So that kind of thing. We took those images where we made the image very dark, but we weren't able to get into the last stage of our observing where we take very, very long exposures. So it's unlikely we're going to see anything astronomical in there, but it's still a pretty valid technology demonstration. It's still a record for however dark we made it. It's the best that's ever been
So
done.
for those 18 hours, you had the
Yeah.
adjustments
Yeah.
done from ground, like you were on it for...
It's like a video game. Yeah, we're flying this thing real time. The whole time we're staring at a big 4 computer screens with all of our telemetry, all our data is coming down in real time. And we're just sending commands, clicking buttons, sending commands up to the balloon. All the communication is line of sight, we're just radios. And it's pretty instantaneous. So it floats for a day, a full night. We still want to observe at night, which is the tricky thing, because the sky is not completely dark during the day. we need to launch in the morning because of the wind. So we have to launch in the morning, and then we have to stay up all day and hope that we don't drift too far away from our home base. And then the sun will set, and then we can start doing the real observing. And so we might get this time we had to come down at 2 a.m., so we really didn't get that much nighttime, but we should be able to stay up all night. And we looked at maybe 7 or 8 different stars throughout the night. So once we track a star, we're limited in how high up we can look because you'll start seeing the balloon at some point. So we have to stay below a certain elevation angle. We'll track a star until it goes above us, and then we'll switch over to another star and just keep doing that throughout the night. It goes by really fast. It's really a stressful and challenging thing to do because you have to show up for work at 2 a.m. the day before and work all the launch procedures to be able to launch at 8 a.m. and then stay up all day and all the next night doing the observing. It just kills your brain to try and make these complicated decisions and deal with things that aren't working properly when you're that tired. So it's hard. We need a much bigger team. There's only 3 of us out there. Sure.
How big is the telescope?
The telescope is 24 inches in diameter, 2 feet. How big is this telescope?
14 inch.
14 inches. All right. So, yeah, this telescope is an interesting design. I can get back to it. I don't know if I have an actual picture of it. Yeah. So it's an interesting design. It's what's called an off-axis telescope. I don't have the actual diagram of how the light works, but the telescope mirror is in here, and the telescope secondary mirror is up here. So the light comes in this way, and it bounces off this mirror and up here, and then down along the side of the telescope to where our instrument is. And this is the chronograph instrument up here, and all the electronics that run it are back here. So what we get by doing that, our telescope here is an on-axis telescope, so its secondary mirror is in the center. And then to do that, you need to drill a big hole in the center of your primary mirror to let the light come back through from the secondary mirror, or you need to stick something in the beam to get the light out. And doing that, you introduce all of these artifacts from the light interfering with all of those truss members or whatever support structure that's holding this telescope together, like we have here. In this design, the beam from the telescope is a perfect circle, and there's nothing intersecting it. So that is really, really useful for this kind of instrument because the optics have to be extremely precise, and the control of the optics have to be extremely precise. That if there were any weird diffraction from all of those edges, it would really degrade the performance. So that leads you to build this kind of telescope. So it's an uncommon kind of telescope. But the space mission that we ended up building will look like this, but scaled up to be 6 or 7 meters in diameter instead of half a meter. Yeah.
So you mentioned that you were swinging underneath the balloon,
Yeah.
but you need to stay on target for a couple seconds. What's your ACS system? Like, how are you controlling the telescope and how are you getting on target?
There's a lot of stuff going on. So up above the balloon, up above the gondola, there's a thing called a rotator, and that does the coarse azimuth pointing, so that can swing us anywhere this way. And then this thing here, WASP, has it's an alt-az telescope mount. It's two motors that it's a gimbal mount, so it can point us this way, or it can point us in this way. So it does pitch and yaw. So the rotator swings us over to get us close, and then this points us at the star. And it's driven by a number of different sensors. There's a finder telescope up here, they call a star tracker. It has a very wide field of view on the sky, so we can see 5 degrees of the sky, so it gets typically 10 or 20 stars that are bright within the field of view, and it can figure out, it does like full lost in space. You can point it anywhere, and it figures out with its onboard software what it's looking at and how to get to where it needs to go. And that gives you the ground truth of where you're pointing, and then bolted onto the back of the telescope is a really precise gyroscope that's running really fast, and it's feeding back into their pointing system. And so they're just adjusting the motor positions really, really fast and accounting for the fact that we're swinging and any other disturbances. And they can do really, really well. They can point this thing to, we hit 0.1 arc second stability, which is better than we probably do on the ground for a lot of telescopes. mean, typical atmospheric seeing is an arcsecond or, slightly less. From here, I don't know what it is. Have you guys measured it here?
3 or 4.
3 or 4 arcseconds? Okay, so we're doing, 10 times better than that, hanging from a balloon in the sky, drifting back and forth. So that's the equivalent of the ACS. It's the telescope pointing system. And then we have a ton of adaptive optics inside our instrument that have to stabilize that even further. So they do 0.1 arcsecond. We have to take that and improve it by a factor of 100 to get down to 1 milli-arcsecond, a thousandth of an arcsecond, which is a ridiculously small angle. But you need that because this thing that's blocking out the star has to be really, really centered on that thing. Otherwise, light will leak out and blow up your image. So, complicated machine. If you want to learn more about it, there's tons of stuff over at the lab if you want to come by.
I'm an introvert with template right now. So
Nice.
Yeah.
Okay.
You was telling me about this.
Oh, good. All right. Yeah, if you want to come for a tour, we're getting this back. This is on a truck right now from Virginia to here. It's going to be here in the morning. So we're going to unload it in the morning, get it back into our lab, and start playing with it again, get ready for the next one. So hopefully they have a good drive.
There must be a tremendous amount of computing that must happen on the balloon. That's
Yeah.
come down to the ground to go back and forth.
Yeah. There's nothing really going back and forth. We're completely, we send commands up, but we don't do any processing on the ground. It's not a tremendous, our flight computer is this box here, or here. It's like a dual core Atom processor, 2 gigahertz. You can build these really cool vehicle computers from this standard called PC-104, where it's these boards that all stack up together. And you can get whatever kind of peripheral you want in that form factor and just stack it up and build this flight computer, and they're all ruggedized. And we do a lot of that stuff in our lab too. We have to take, what we do is, we're not a space mission, we don't have hundreds of millions of dollars to build our own electronics. We buy a lot of off-the-shelf parts and then make them work in a vacuum. Like I said, you're above 99.9% of the atmosphere, so it's a vacuum for all of its purposes. It's space. So we have to take these electronics and we take them all apart. We catalog all the parts. We figure out what might not work in a vacuum. Most of that stuff we just cover in glue to make it not know that it's a vacuum. It's a pretty cheap trick, but it works really well. So if you have things like capacitors that are filled with goo, just cover them with glue and stick them in a vacuum chamber and see if they still work, and they usually do, and that's what we did. But we have to do that for everything that we buy and make sure it's all tested, and we have a big vacuum chamber in our lab where we stick all this stuff in there and pump it out and make sure it doesn't overheat, and there's a lot of... This thing has 100 temperature sensors all over it. You can see here these little black dots. We measure the temperature throughout the entire truss, and we have a graduate student who's trying to build a model of the whole telescope and figure out how cold it gets and where it gets cold and how it shrinks as it gets cold. It's a very challenging thermal design problem. So there's just a lot of aspects of engineering and optics and science that go into the building one of these things and solving every little problem that you run into.
Well,
What else?
anyone else?
Is it dark?
It's almost dark.
Almost dark.
Thanks very much, Chris.
Thank you guys for listening. It's a pleasure.
Good luck with your next mission.
No, thanks. Yeah.
Liam, are you going to tell us about what we might see tonight in the
Yes,
sky?
I am.
All right.
All right, so we can just talk about what we might be able to see tonight. So one thing, Saturn, it rose at like 12:50 today, this morning, so we'll be able to see it. It's 9.5 AU away from the sun, so as Chris said, 1 AU is the distance between the sun and the Earth. It has 62 moons, Titan's the biggest. With our telescope, with the camera on, we can see the moon and we're able to see the rings of Saturn. So this is cool. We have Jupiter will also be up. It's 5.2 AU away from the sun. It has 4 moons, which are able to see through the telescope. It's really nice. Mars is also starting to rise. So it rises at 6:20, so it's only 5. So it's not up yet, but we might be able to see it. 5.5 AU away from the sun. There's 2 moons, and also currently there are 5 rovers on Mars. Cool. For deep sky objects, what I might be able to see is the hidden galaxy. So it's a galaxy that's behind some dust near the galactic equator. So you can see it, but the reason it's called hidden is just because it is slightly dimmer than it would be, and if it weren't for that dust, you would be able to see it with the naked eye. Probably not naked eye here because it's very bright out, but in the non-light polluted area. And it's 7 to 11 million light years away from us. We have NGC 7331, not as fun of a name, unfortunately. It's another galaxy, 40 million light years away. Interesting thing, this one is like the center bulk area of the galaxy rotates in the opposite direction of the outer rings of the galaxy, which isn't as common of a thing to happen. And there's been multiple supernovas observed in this galaxy. I think 2014 was the last one. We got the blinking planetary nebula, which planetary nebula doesn't have anything to do with planets. When a red giant dies, it can eject like some gas outwards into the star. It becomes a white dwarf, and you can see the gas going outwards. The reason for the blinking nebula is apparently if you look directly at it through a telescope, the brightness of the star affects your eye, so you don't actually see the planetary nebula. But if you look away from it, your eye adjusts for the darker, and then you're able to see it. So as you look around, it kind of blinks in and out of being able to see. I've got Ring Nebula, which is another planetary nebula. It's 2,000 and a half light years away from us. And it's 1.3 light year radius from that distance. We got some star clusters. Got the Great Pegasus cluster, so a globular cluster. It's a bunch of stars all really close together. There's somewhere like 100,000 stars in the cluster. It's one of the denser ones that we know of. It's also one of the older ones didn't get the age, I think it's a couple, like 21 billion years old, I think. Inside of it, it has a planetary nebula, and there's like 4 star clusters that we know of that have planetary nebulas inside of them. We'll really be able to see the planetary nebula, but it's cool. And then we have the Dragonfly cluster, which is an open cluster, so the stars aren't as densely together, but they were all formed around the same time. And it's 7,000 light years away. And I believe if you have questions, now we can head down to the observatory.